All right, thank you for a very kind introduction and for inviting me over. Already had a few very good, stimulating discussions this morning. Looking forward to meeting many more of you in the afternoon. So I made the drive up this morning from Rochester University, where, as you said, I have my lab working on superconducting circuits. And I was told that this is a very broad audience. I think some of you are really experts in superconducting circuits, while others have a more broad overview. And so I tried to keep this broad, and then towards the end have a little bit more technical detail for some of the experts. And we'll see how far we get. And I wanted to preface this by saying that if you have questions along the way, please just ask. I can adapt and skip a few slides if needed. So the idea is that in our lab, we are interested in studying these superconducting circuits that you could see right here. And the special sauce that we add to this is that these superconducting circuits give us a cosine-like potential, and we make a cosine that's really deep. And then by making a really deep cosine, we can trap many states in there, and then we use those states for quantum computation and some fundamental physics. That's the basic idea. Since I was planning to do a general intro, I'm also teaching quantum mechanics this semester, and I'm telling my students that there's two problems that every quantum mechanics student should understand and learn really well. So this is the audience participation side, where I would ask you, what do you think these two quantum problems are that everybody needs to understand?
Harmonic oscillator.
The harmonic oscillator, yes. And what's the other one? Two-level system. Thank you. You are doing the best of all the universities where I've done this. I don't think that there's one single answer. Like, people like the infinite square well. I like the infinite square well. For the context of my talk, if you understand these two, you can understand many of the concepts in quantum mechanics. So these two are very distinct, right, in two ways that are important for my talk. One of them is that the harmonic oscillator is infinite dimensional and is linear, because every energy transition is the same value. Whereas a spin 1/2 you could think of as the most nonlinear system if you wanted to, because it has one transition that's completely isolated, but it's finite dimensional. It just has two states. And what we wanted to do in our experiment is to argue that there's maybe one intermediate type system that combines kind of the best of both worlds of these, which is a large angular momentum spin. And that's the topic of most of my talk for today. So what we did is, we did not actually make a large angular momentum spin. We made the kind of like a quantum circuit that operates in the microwave regime here, that has a spectrum that can be treated as a finite dimensional spin with some quantum number J. And the reason why we do that is because we can go to higher dimensions, which gives you a lot of computational benefits, but then also it has a high nonlinearity, which makes it easier to control. To a certain extent, this is my talk. And so like, if you understand this idea that we did this in the circuit, then that's the message that I wanted to convey. I'll get into the technical details, of course. I'm not stopping here. But I wanted to give a little bit of a broad overview of why we do this, why we are interested. And to me, this always starts with this idea, as I'm a quantum physicist, but also a little bit of an engineer. And so I was doing my PhD with the idea that this idea of quantum computing is really interesting. And that then, for an experimentalist, that starts with trying to be able to take an experiment where you can at large scale control quantum systems and have individual control. Right? That individual control is crucial because, I mean, many technologies in our computers or lasers right here are actually large scale quantum systems, but we don't have individual control over them. And so that is the general challenge that people like me who are doing experiments on these kind of things face. This started originally, I think, with the idea of Richard Feynman, that he was saying that if you want to simulate something in nature, you better make it quantum mechanical. And then maybe a decade afterwards, there were these two canonical papers coming out of Bell Labs that were saying that if you can control large quantum scale systems with an individual at an individual level, you could maybe do quantum computing with them. So why did Feynman say that simulations of nature should be quantum mechanical? It's because of the exponential complexity that comes with quantum theory. Many popular media actually get this wrong. So I have one slide that, if you have not thought about this very deeply, that just makes the connection between quantum mechanical space and classical space. So generally, when you compute using either classical states or quantum states, your state space, if you do this in a binary fashion, always scales exponential in both cases. The amount of states in your system is 2 to the power n, where n is the number of bits or quantum bits that you add to your system. Physically, right, classical systems, the bits can be represented by magnets or current or light. And quantum mechanically, we have our information represented by quantum degrees of freedom, like spin, atoms, or photons. The real difference, so importantly, both of these scale exponentially, right? The real difference is that at any given time, a classical system is only in a single state that can be represented by a single n-binary number, whereas a quantum system of n qubits can be in some kind of superposition, there can be entanglement, and in general, if there's no simplifications possible, it requires 2 to the n complex numbers. And that's the exponential complexity that potentially gives you the benefit of computation when you use quantum systems. And also that is the exponential complexity that in general makes it hard to simulate very large quantum systems. Many people will just start here and then say that that's it. But that's true for classical systems as well. Rather than giving a state-of-the-art overview of the field right now, I want to actually start really early on, after these ideas of quantum simulation and quantum computing started, because there was a lot of early skepticism about this general idea. So when I think about the quantum computation, I think of some operation in some big Hilbert space, where the challenge for us is to engineer a system Hamiltonian and act it on a wave function in such a way that the time dependence of these coefficients of the wave function interfere in a way that helps our computation. That's a general challenge. However, it was very early realized that there's a worry which comes with the decoherence. So I have here a picture of an article that was written by Serge Haroche and Jean-Michel Raymond, I think somewhere in the 90s, that were saying that because in reality, you're never going to couple just your system, but you will always have some kind of environment. And then the detrimental interaction of that environment with your system is going to lead to quantum decoherence. It's going to make this exponentially hard to do. They were not wrong, but what they said was that this cannot be fixed. And around the same time, in 1995, Peter Shor came up with a solution to this problem, which is quantum error correction. So rather than doing the computation in the exact Hilbert space that you want to simulate, you can redundantly encode, say, a single quantum bit into multiple quantum bits. And then there is a way to find out if errors happened without perturbing the quantum computation. The authors of this article knew about this, and they called this some kind of watchdog strategy. And what they said was that surely this is a beautiful idea, but if you are going to do this watchdog strategy that we now call quantum error correction, those operations will need to work 100% of the time. And if they do not, they are never going to beat the decoherence. So Peter Shor had to think about this for a little bit, and it took him 1 year to come up with a protocol that was called fault-tolerant quantum computation, which was the first proposed protocol that proposed how you could do this quantum error correction even if your gates are faulty. And so in general, when we think about quantum computation right now, there is this idea that there are certain protocols that can tolerate errors, and even errors in the operations that try to correct for the errors. And then under certain assumptions, if you make your quantum computation more redundant, the error should be able to go exponentially down. And that's the idea of fault-tolerant quantum computation. And that's what many groups in the field are after right now. So skipping forward a little bit to the actual platforms that are trying to do this, maybe in the early 90s to 2000s, the first qubits were demonstrated in many different platforms. I always like to point this out because actually some of the very early skeptics of quantum computing got the Nobel Prize for showing that they can actually manipulate some of these quantum systems at a level that I think their earlier skeptical paper would not have imagined. This is an example from actually the Wineland group where they showed some of the first examples of quantum error correction that were demonstrating the principle but not fault tolerant. Very recently, just last year, the Google team and maybe a few other experiments as well have demonstrated that they can now make a chip. This is superconducting circuits where they do a particular quantum error correction code called the surface code, where the way that you can understand it is that they encode a logical qubit in a 3x3, a 5x5, or a 7x7 grid. And if you plot the error rate as a function of the code size, you can see that they exponentially suppress the error, which is the key requirement for fault tolerance. So that's really demonstrating at a very small scale that this idea of fault tolerance is possible. There's a lot more to say about the state of the field right now, right? There's many companies who are going into this. There's a lot of optimism. There's a lot of false optimism. There's a lot of hype. I don't want to touch upon that too much, but since this is a general audience, I want to point out that like, don't believe everything you read. But at the same time, if you read the skeptical articles, I do like this, this historical perspective of just look at where we were just a few decades ago and look at where we are right now. There's still a very long way to go, but they demonstrate is barely a single logical qubit, and to do something useful, you really need many more. But in a nutshell, this is how I think about the quantum information processing story as developing, and I think we are on this path to do make these systems work even better, start to do useful things. And if we can do that is a big question. This is where I want to start to motivate a little bit the take that we have on this problem, which is that so far most experiments, not every experiment, but most experiments kind of take some physical system that's made up of two-level systems, so our spin halves in the beginning of the problem, right? And then they do universal quantum computation by stringing these together with local gates and entangling gates. And while every platform has its own benefit or challenge, in general, it's just really hard to do entangling operations between these qubits. There's one example of something that looks like fault tolerance that goes about this problem a little bit differently, because they don't encode in binary systems or qubits, but they encode in harmonic oscillators. And this was pioneered by a few groups, including the Yale group, that have demonstrated that if you encode not in a collection of spin 1/2 particles, but in a single harmonic oscillator, and if you are able to do good quantum operations on that harmonic oscillator, then you can define quantum states of that harmonic oscillator that are also able to correct for errors. And they were able to show that with that, you can extend the logical lifetime of a logical qubit with schemes like this. And I'm highlighting this one because this is one of the paths that uses beyond binary encodings to achieve the same thing. Now, why is that a good idea? In simplified language, I think that is because you don't need as many entangling gates, right? You just use a single degree of freedom of an harmonic oscillator, and rather than needing to do many difficult entangling gates between qubits, you just encode your information in a single degree of freedom that's higher dimensional. And that is the same spirit of what we are doing in our lab, except we are not using harmonic oscillators, but we're using nonlinear oscillators, where the benefit is that this nonlinearity naturally gives us good control. Whereas for the harmonic oscillators, you actually needed to add a nonlinear system to get your universal control in there. So that is what our lab is interested in. We have these superconducting circuits that are nonlinear oscillators. We like to couple them together and operate within a single one. And once we are able to do that, we are thinking that with these, beyond binary encodings or qudits, where D is some number higher than 2, we can do more efficient circuit compilation. We are thinking about analog simulation. We're thinking about ways to do error correction in the system, and maybe also ways to do metrology. And that's generally what my lab is interested in. For the purpose of today, I will show you results of just a single one of these nonlinear oscillators and how we can measure it and operate it efficiently. And then I'll have a very brief outlook looking forward. So that's the plan for today. All right. So the system that we are using is superconducting circuits, where I'm not so sure everybody's familiarity, so we'll have a very brief introduction to how you think about these. These are quantized bosonic modes in superconducting circuits, where I like to think about a classical LC circuit, where you have a magnetic field in the inductor, you have an electric field in the capacitor, and you get a resonance frequency 1/√LC. You can quantize this, and then it's kind of more convenient to work with the flux across the through the inductor and the charge across the capacitor here. And then with these quantum variables, you can show that if you quantize these degrees of freedom, you get these natural raising and lowering operators that belong to the quantum harmonic oscillator, which is the other canonical problem that I started my talk with. However, no, okay, yes. So we can make these in the lab. They don't look quite as lumped element as this. In practice, what we do is we make these out of superconductors. This is an example from our lab where we make a coplanar waveguide, which if you're an optics person, it's just like a fiber, but on 2D and for microwaves. The coplanar waveguide has a ground plane on two sides and a center conductor, where the electric and magnetic fields are now distributed along this waveguide. And they go here around and between the center conductor and the ground plane. And we make this with a superconductor on top of silicon. If we then create boundary conditions, in this case, we make a lambda over 4. So we create a short to ground here and we leave it open on this end. You get a resonance circuit that its lowest harmonic mode can be approximated by an LC circuit. And that is the harmonic oscillator that we work with. And we just work in a range where all the higher harmonics can be ignored. We made these actually in the lab. This is an example from our lab in Rochester, which we made during COVID. We were very proud of it. It's by far not state of the art. But if you're seeing data like this for the first time, we make, in this case, we make 7 coupling to a single waveguide, and then we change the length of these resonators slightly, such that their resonance frequency is slightly different. Notice that we work in the gigahertz regime here, and what we can do is we can very accurately tune the frequency of these resonators here. And you see if we then excite this with the resonant pulse, we change the frequency, you see the amplitude and phase response here, showing that all the resonators are there. And then if you extract the coupling factors, what you can show is that you can get these into a regime where they couple much more strongly to the external waveguide here than they couple internally to the loss. And some of these numbers are much better in the field right now. But that means that you can do circuit QED at a level where your coupling is much stronger than your loss typically. And that has been the success of this field in general. However, everything I've told you so far is just a quantum harmonic oscillator. And as much as we love the quantum harmonic oscillator, it's actually the most classical quantum system that you can have. One way to see this is that if you actually have if you just linearly drive a quantum harmonic oscillator, you look at the states that you get back, the stronger you drive, the more classical it looks like in all its properties. So to do the kind of quantum information protocols that we are looking for to get these non-quantum states, we want a non-linearity in the system. And the way that we engineer this, one way to engineer this, is to add what is called a Joseph tunneling junction, which has not a linear inductance, but this sinusoidal dependence of the current on the flux. In a circuit, we denote it by this cross right here. And in practice, this is an example from Lincoln Labs, who made one for us. This is a piece of aluminum. There's aluminum here as well. And in between, you can't really see it, but there's a very thin layer of aluminum oxide. And that makes a tunnel junction. Cooper pairs can tunnel back and forward. And that gives rise to these Josephson relations. That gives us a nonlinear inductance and therefore nonlinear potentials to get our quantum states. The way I think about this is in the end that there's some quantized modes, and I don't really think about the microscopics anymore. But I do like to point out that there's 2 types of qubits that you can make with this nonlinear element. One of them is a flux qubit that encodes quantum information really in the flux through a superconducting loop, where the qubit is really encoded in current going in clockwise or counterclockwise, giving us a flux pointing up or down, and then that can be your qubit. Alternatively, you can make what's called a charge qubit, where the encoding is really the number of electrons on one end of the capacitor or the other end. And while these are historically the first ones that were made, and they're intuitive to explain, at least to me, they're more sensitive to noise. And so in the field, we have shifted to what's called a Transmon, which essentially looks like a charge qubit, but we tune it in a regime where the energy in the inductor or the Josephson junction is much higher than the energy stored in the capacitor. And then you get level diagrams that I will show in my next slide that are very insensitive to the charge noise. And that makes them a very nice thing to work with. Although in the field, people are exploring even better circuits. The way that this looks like in the lab or on a chip is something like this. Note the scale here. This is, we're doing quantum physics, but it's not the size of your usual atomic systems. And the reason is that we work in frequencies of gigahertz, which is very long wavelengths. That means that we can make our systems really big, which is convenient because it's quote unquote easy to fabricate. Or maybe to say the challenge of making really small systems to get interaction strong is not something that we have. So this cross right here is the center is the pad of one of the capacitors here with respect to ground. So one of them would be this pad of the capacitor, the other one would be this one here. And then right here you can see that there's something connecting them, and that's a junction shorting the capacitor pad to ground, which makes this effective LC, nonlinear LC circuit. And we get these cosine potential with the energy states in there as a function of phase. We then couple two of these together. So we have a transmon and we couple it to a cavity, which essentially implements, if we do this in the dispersive regime, where the resonance frequency of the transmon is different from the resonance frequency of the cavity. And we get a system that looks a lot like a typical AMO James Cummings Hamiltonian. And so you can think of this as an effective atom coupled to a cavity. So we write down the Hamiltonian like this. If you truncate the qubit or the transmon to the lowest two states, you get these Pauli operators here. And because this is dispersive, because they're very far off resonance, they don't swap energy, but you just get a shift of the resonator here, depending on the state of the qubit. That is something that we can use for readout. The first demonstration that you can get this into the very strong coupling regime, meaning that a single excitation of the field changes the qubit state by a lot compared to the noise, was shown in this paper by the Yale group in 2006, where they do spectroscopy of the qubit. And essentially they use the qubit, so they tune across the qubit frequencies, and they see that when they drive the cavity with more and more photons, more strongly, you get these distinct peaks, and every peak here corresponds to the qubit frequency when an additional photon is in the resonator. And you can see very beautifully that you get all these peaks at the same time, and that's because you drive it linearly and you get what's called a coherent state. And most importantly, the shift per photon in the resonator is large compared to line width here. And that means that you're in a strong coupling regime. And it's kind of amazing that you can do this on the circuit. If you translate this to doing this in AMO, this is often really difficult to do because you need to overlap really small things. So we can also use the same effect in the opposite way, where now we do spectroscopy of the cavity depending on the qubit state. And that's what we use for readout. So this is an example of scanning across a single resonator, plotting the phase and the amplitude response when the qubit is prepared in the ground state. We can now excite the qubit by resonantly driving the 0 to 1 transition and do the same spectroscopy. And what we see is that the resonator shifts a little bit to the left, and we can engineer by how much it shifts. If we then send in the tone and we look at its reflection and we look at the I and the Q quadrature of the reflected field of the cavity, every point here is a single measurement where we do this. Every time we do this, we get a little bit of noise. That's partially the quantum noise and partially the instrumental noise. But importantly, what you see is that in the IQ plane, our demodulated signal lands noticeably different location for the qubit in 0 or 1. So what we can do is we can draw an imaginary boundary here, and then we can distinguish the qubit with a single shot readout of the cavity. All right, so all of this, what I've said so far, is standard circuit QED instruments. What we are going to do is we're going to use the same circuit, we're going to tune it into a different regime, and we're going to use these tools for qudit computation. The way to understand the circuit a little bit better is that it's so characterized by this ratio EJ over EC, where the larger you make EJ at a fixed frequency, the deeper your transmon potential well is. And the larger EJ over EC, the more flat, depending on charge, your energy levels become. For the qubits transmons, most people work in this regime of EJ over EC is around 50, where you can see that the first excited state is relatively flat with charge, but the higher states are kind of wiggly. And also there's not that many. And so we went into an EJ over EC of 250, where we can see many more states, and we get very flat bands, even for the higher qudit states. There's no such thing as free lunch, not with the transmon either. And this comes at the cost of reducing the anormalicity. And so what I plot here is the charge dispersion, which is how wiggly every excitation is, as a function of EJ over EC for the first and the second and all the excited states. And you see that if you want to make the charge dispersion small compared to some other energy time scale that's there, the higher the EJ over EC, the more levels go below this bound. It comes at the cost of reducing the anormalicity, which is the difference between going from 0 to 1 and 1 to 2. And so for a really small anormalicity, this actually recovers the quantum harmonic oscillator. That's not quite true, but it's not quite true in the circuit. we're making this more and more like a quantum harmonic oscillator. So what I hope to convince you by is that we only sacrifice a little bit in anharmonicity, and we gain a lot in how many levels we can pull in. And we have some ideas of how to go around this trade-off later on. So that's the idea. We made a Transmon with very high EJ over EC, or actually we made a few that are varying. We did this together with MIT Lincoln Labs. They have this foundry surface where we designed a chip. This was work done by my two PhD students, Ray Parker and Zihao Wang. And we designed this chip. They benchmark their systems. They have nice long coherence times. And so they package this up for us, and we can do the science by just driving this and by designing this in a different parameter regime. These numbers are a little bit for the experts. I'm more than happy to show this after if you're interested. But maybe most importantly, what you can see is that we change EJ over EC from about 50 to 200, about 300. And then we reduce the anharmonicity from 250 to 120 megahertz. And you need to compare that to a qubit frequency of 5.4 gigahertz. So it's still very largely separated. You can still do a rotating wave approximation on the drive, and that works really well. So the first thing to do is then see if we can read out this system. And to do that, we actually...
Okay, sorry, it's a small technical question. But here you're driving the Transmons through the feed line?
Yeah.
Okay.
We have chips later that have control lines, but for this, we are driving through the control line, and it works fairly well. And most of this work is done on qubit number 4, although we do mix some of the data here. More details in the paper if you're interested. So then we can prepare all the excited states, and we can do spectroscopy of the cavity. And you can see that this works fairly well, provided that you have a broad bandwidth microwave generator that can generate all these tones. And so we can really resolve, in this case, up to 10 states, which is roughly what you would expect for an EJ over EC of 250. So we'll show, because roughly this is the ratio of the, you can derive this as the ratio of the depth of the potential divided by the rough distance between every transition. And then you can see that the number of levels that should be in the well should be square root EJ over EC, half EJ over EC, and that roughly matches what we expect. So here we showed that we can resolve up to 11 states. I wanted to make the connection back to the plot I showed earlier of this very strong interaction in circuit QED, because we're kind of doing the mirror image of that experiment. Here, what they show is that they can do spectroscopy of the qubit and resolve the cavity photon states. Here we are doing spectroscopy of the cavity, and we can resolve the states of our artificial atom, of our Transmon. And crucially, note that here they, for reasons I don't fully understand, the x-axis goes very high to very low, and we do the opposite. The shift is actually the same direction. But more importantly, we prepare Fock states, whereas in this case, they only prepare coherent states. And so that already shows the Fock state is actually a more classical, more quantum state that you can use for encoding quantum information. So the fact that we can prepare all these individually kind of already shows that we can do types of quantum operations that you could not do if you do the opposite. Yeah.
Quick question. So what should I take home about the line width on these individual plots? Because the line width is around the same as the shift in each one, and then it starts to wash out as you get to the high states.
Yeah.
How do I think about that?
So first of all, the line width is the line width of the cavity, and that is mostly dominated in our, there's some technical details, but it's in large part dominated by the intentional coupling to the external environment. So this is just the kappa external that we engineered. The observation that the line width is roughly the shift is by design, because that turns out for qubits, that's actually the optimal regime depending on how you do your readout, but you can prove that for some readout schemes, that's optimal. So you can design the shift per photon to be equal to the line width, and then you balance some trade-offs optimally. So it's by design.
Yeah. So, but if I want to think about, like, you encode some state that has excitations at a bunch of these levels, is there a clear way of decoding all those things?
Yes, that's 2 slides from now. I'm going to show that's the readout part, right? So that's decoding the readout signal to distinguish these states.
Okay.
Yeah, that's coming up. That's coming up. Yes, it's a great question. And the fact that they wash out a little bit has to do with charge noise of these. And also this line width, we were actually limited by the spectroscopy in these particular plots. So we figured out a lot about these later on, but not. Yeah, okay. There's more technical details, but that's maybe not the most important part right now. Right, so actually this is the question. Can we now do actual readout of all of these in a single shot? So first of all, this is just to show again, this was the device we had. And for this one, this is the potential well. This is actually 2 scale. So this is using a package. I had citation earlier, I think, by University of Northwestern, Jens Cox group. Some of the pioneers in this field, they have this nice package that can allow you to calculate these levels and the potential. I really recommend, if you're interested, to download it and play around with it, because it's really very nice and intuitive. So we use that package to make these plots. What you can derive is that the height of the well is 2EJ, whereas the frequency can be approximated as the square root of 8EG-EC. And that gives you the expression for the number of levels in the well. This is just the same data that I showed earlier, but now the question is, if you now want to do readouts, so you want to have a single tone parked somewhere in the spectrum, and you want to distinguish all these states, what happens? And the first observation is that if you have a single tone, you can maybe distinguish a few of these states. Like in this case, you can distinguish maybe 0, 1, 2, and 3 with a tone parked at this frequency. Note that this is just a different representation of the same data here. But then the higher lying states, they kind of overlap at this frequency, so you cannot really distinguish them. So then the question is, how do you successfully read out all of them at the same time? And intuitively, you can see that you need to add more tones. But then the problem is, if you add more tones and you do this sequentially, so here we just send in a bunch of these tones and we demodulate them at their own frequency, we make the IQ plots. Now the problem is, what if these tones actually disagree? What if one of these tones, what if this tone says that we are in state 3, but this one tone states that we are in state number 2? And that actually turns out to be a very significant error if you just naively demodulate every tone by itself. But so what we did is we have 2 approaches to tackle this problem. The first one was to recognize that really this data does not live in 3 separate IQ spaces, but really it lives on a 6-dimensional space where you can demodulate the quadrature Q of 1 with respect to the I quadrature of the second one. And then you get a 6-dimensional space that then you can fit Gaussian model to. And actually that works fairly well. So that eliminates a lot of this ambiguity between the individual tones. And then you can look at correlations between 2 tones that allows you to distinguish on average with 85% fidelity in this particular data set, the tones, which already is pretty good, I think, for 10 states here. This is a table that shows when we prepare the state and we assign the state, it has a very distinct error channel, right? The main dominant error here is we prepare state n and we read out state n-1. And that's because of energy relaxation during the readout. And crucially, what we have done here is we have integrated the readout signal. So we have a readout tone of a certain length, we integrate it and we demodulate it. And then we only have a single point on our Q space for every readout tone. But in principle, we are collecting the data during the readout, and you can use that to look at the decay as you are reading out. When I say you, actually, we made a machine do this, so we fed this into a neural network, and then what we showed is that when you do that, you fit the raw voltage traces, and it can actually get a higher fidelity. And what you can interestingly see is that this T1-like behavior is much less pronounced, and so that means that these neural nets can actually distinguish T1 decays during readout and get a little bit higher fidelity. Yeah.
So that's just to make sure I understand carefully. So so the measurement operator for each of these tones separately commutes with all of the diagonal elements of the Hamiltonian so that you can read out population. Like, how do you do tomography? It's just going to be a horrible thing to do.
That's the next slide. Tomography is the next slide.
Oh, okay. Yeah. So I guess my question is you're not messing up states when you're applying multiple tones.
So those are 2 different questions.
They are, but yeah.
So the tomography. So this is a projective measurement onto the number basis. Yeah. But it's not quantum demolition.
Yeah. Okay.
Which I've not shown.
I'll take your word for it. That's fine.
It's not, and that's something that we're working on. For qubits, you can make this quantum non-demolition. For qudits, it's going to be more difficult. But it turns out that you don't need it to be quantum non-demolition to do tomography. And actually, the tomography is going to be the next thing. Essentially, what you do is you combine this projection operator with spin displacement pulses that we have generated, and then you can reconstruct the Wigner function.
Sorry, but is there any meaningful concern that it may be non-QND?
Yeah.
Outside of like the ionization stuff, I mean, like I would have expected this is still just multi-level dispersive readout, so
Yeah.
it should be just QND and
Yeah.
fine.
Yeah,
Okay.
yeah. No, I don't think there's any additional concerns. Yeah, we can talk more about later about details, but I think just the problem is that it becomes less QND the higher you go, and so to the extent that the qubit readout was not QND, this is going to be even less QND, and that's something that.
And is my intuition for that as you go higher up, your nonlinearity is getting weaker and weaker?
No,
Or
actually,
is there
that's
another fundamental reason.
there's a few fundamental reasons that I probably won't get to those, but very briefly, you get bosonic enhancement, which is just coming from the fact that your raising operator has this square root of n scaling, and that means that the matrix element that causes loss actually scales your decay rate as you go up in the excitation to bosonic approximation linearly, which is not specific to qudits. That's true for harmonic oscillators as well. Just the higher up you go, you're linearly more likely to lose photons there. And that means that if that happens during the readout, then you're not QND. And that is something that we do not get around, but that's also something that bosonic operators do not get around. I have some data on the noise of how that scales as well. Questions about this readout? I mean, if there's interest, I'm happy to talk more about it. No. All right. So that is how we can prepare and read out up to 10 states in our Transmon Qudit. The next question we wanted to ask is actually, how do you efficiently control single qudits? And I made the point that qudits are interesting because they give you some efficiency gain, but that is really based on the assumption that it is easier to control a single qudit than it is to entangle many qubits. And so it's really key to show that you can do good single qudit control before you want to make the case that this is a useful thing to do for quantum information. The common approach until fairly recently has been to do qudit gates by Givens rotations, which is just sequentially driving neighboring levels. And then what you can show is that you can do arbitrary, for instance, qudit DS4 rotations, SU4 operations, by just stringing together these Givens rotations. But just by looking at this decomposition here, you can kind of tell that most of the time the system is doing nothing. And that leads to an inefficiency that is shown by the order of scaling here, which is you need d squared Givens rotations to do a universal qudit gate. And what we have shown, and actually Vala's group as well, and Andrea Morello's group has shown as well, is that by doing operations that look like large spin rotations, you can actually do universal control with order of d pulses. And the idea really stems from thinking of this system not as a truncated bosonic operator, but as a large angular momentum spin operator, where the analogy is that the harmonic term looks like a Zeeman term, and you can think of the first order approximation of the cosine potential, the kernel linearity, as the quadrupole splitting, and that actually for some parameter regimes gives you the same spectrum. And then inspired by how you think about spin, in our case 7/2 systems, we can engineer rotations that are both more efficient for control and also actually efficient for doing Wigner tomography. And even more so, it defines a phase space that is very nice to look at. So it's a very natural way to represent the state of the system. And before I go on, actually, Vala visited Rochester a year and a half ago now, I think. He was presenting some of his work, which was not along these lines, but then he said he had like a really cool project that was kind of secret and he didn't want to tell us about. And then I thought I had a really cool project that was kind of secret and I didn't want to tell him about. And then we shared notes and we actually found out that we came up with the same idea in a different system, which is to use these kind of spin coherent, or like depending on how you want to call them. And then we compared notes with Andrea Morello, and he also came up with this independently with actual large angular momentum spins. And so there were 3 groups working on this simultaneously. I just wanted to point it out, especially here. You know, it's I think it's a fun story that we all came up with in vastly different systems, the same unitary operations. So we were very happy with that. I'll give you a brief introduction to how we think about them. How close to 45 should I end?
You can use more time.
Okay, how much more time?
You can go till 1.
Okay. I probably won't, but good. All right, so this is the most mathematical part of the talk, where I want to compare the phase space representation of an harmonic oscillator and the natural operators to our large angular momentum spin operator. So the operators you can write down either in X and P or in A dagger A, and then it's very natural to think about the displacement operator as an exponentiation of a complex combination of A and A dagger. And what it gives you is it gives you some translation in the complex plane, which is a displacement. And this is the very natural operation to define a quasi-probability distribution, the Wigner function right here, where you take your state and you displace it, and then you project it on the parity operator. And this is a function, again, that is a quasi-probability distribution that can represent the state in this fashion. And note that for a quantum harmonic oscillator, this is very naturally defined with respect to the displacement operator that you have. And for this to be a very nice phase space, you actually need a combination of two displacements to give you a new displacement. Now, crucially, if you just naively take the matrix elements of the bosonic operator and you truncate it, then you do not get a phase space representation. Because if you truncate the bosonic operators and you take two of them, then they do not give you another displacement in the same phase space. So then the linear algebra properties actually break down, and that is not a good way to think about it. Instead, the mapping to a large angular momentum spin system is very natural. So you can define your angular momentum operators, Jx, Jy, and Jz, and in similar fashion, you can define your ladder operators of your spin. And then you can define the displacement operator in exactly the same fashion as an exponentiation of J plus and J minus. And what you get are SU2 type rotations on the large angular momentum sphere. If you do this for a dimension ds2, you recover the Blok sphere and you get your Pauli operations back. But you can do this for higher dimensions as well. And maybe your your instructor for quantum physics make you do this. Definitely my students are going to do this. So what you get is a phase space that can be defined with respect to this Wigner function that is displacing this large angular momentum spin with angles theta and phi, that in this case, I should stress here that these bounds are just because I didn't turn off the frame for the plotting. Like this is in principle an infinite space, right? But what you get here is a displacement that is characterized not by an infinite parameter alpha, but you can also parameterize it by these two polar coordinates, theta and phi. And that means that the phase space here is not an infinite plane, but it's actually a circle, but it's the surface of a circle. And then you can do a polar projection to plot this onto a 2D circle, where the North Pole goes into the middle and the South Pole goes on the edges. And here, this edge is meaningful. It's actually the bound of phase space. It's kind of like an holographic projection, if you want to, of the surface of a sphere onto a plane. And then with this math, you get similar Wigner functions that really, qualitatively look very similar, which intuitively makes sense, because if you make large angular momentum, if you make that really large, then in the bottom it just looks like a harmonic oscillator. Only if you reach the boundaries here, it starts to look different in a very meaningful way that I will not touch upon today. Yeah, so that's why we like these raising and lowering operators, or spin displacements as we call them, SU2 rotations of large angular momentum spin. In the lab, the way that we make them is we apply resonant tones to each separate transition. That effectively gives us matrix elements compared to only like the 0-1 transition or the 1-2 transition. And then if we do that with an amplitude that is low compared to our anormanicity, we can do a few rotating wave approximations. And we can essentially make drives here where we can tune the matrix elements by just tuning the amplitude of the drive. This is fairly standard in labs if you are used to doing quantum experiments like this. And so just by turning on drives between only 3 levels or 5 levels or 8 levels, we can do this as a function of time and show that we get these SU2 type oscillations, which again, for DS2, this would just be Rabi oscillations on the Blok sphere, but this is the equivalent of that in 3, 5, and 8 dimensions. And what you can see is that it rotates from 0 here all the way to 7, but then in the middle here, you get like some superposition of all of these states, and that's actually a spin coherent state, halfway on your large angular momentum Blok sphere. Because we have the projection operator and we can actually measure every level here, we can also reconstruct not just every population, but the expected value of Jz. And we can plot that for every point, for every dimension. And this is showing that you really get these nice SU2 oscillations where just the expectation value of Jz increases with the dimension of our artificial spin. Right, this is the tomography part. So I've now shown you, I've defined the Wigner function here, and I've shown you that it can be defined in phase space as a function of theta and phi by this operation mathematically. And in the lab, I've shown you that this is the projection operator or some version of the projection operator, which we get from readout. And these are the displacement operators that I've shown you we can engineer. And then we can prepare arbitrary states and reconstruct the Wigner function by implementing these displacements and measuring the parity. And that allows us to actually, in data, reconstruct these Wigner functions for different initial states. And if you're really interested, you can also plot a density matrix if that's something that you're more familiar with. There's a mathematical way to go from these Wigner functions to these kind of Manhattan-style plots from the top that are maybe more familiar if you're just looking at quantum information papers and density matrices. So this very naturally gives a way to do tomography combining these displacement gates and the readouts. Did that answer your question or no? Yeah, good. Okay, so we can prepare these states, we can control them, we can measure them, we can visualize them. The caveat here is that by restricting ourselves to SU2 operations, we've actually restricted ourselves to the most classical version of the large angular momentum spin. And that means that we cannot reach full Hilbert space with these operations. To fix that, we add something that's called a virtual Z-gate, which is very standard in standard quantum computation language, except they usually do it for qubits. Without going into too much of the detail, every drive here is making a single matrix element of our displacement gate, and tuning the amplitude tunes the amplitude, but we can also tune the phase, and that tunes the complex factor of that matrix element. And that effectively is the same as doing a Z rotation, but we can kind of do it individually. So we can do individual given Z rotations here, and we combine them in any way we want to, which effectively allows us to do what's called in bosonic language a snap gate, which is just giving an arbitrary phase that we can tune by giving the microwave pulses the desired phase. And this is a really difficult gate to do when you're working with bosonic modes alone. For us, it comes for free by just updating the microwave thing here, which, we have microwave generators. They come with 12 or 14 bit. So we have very high resolution in determining the phase here, which is just a software thing. It's not even physical. So these are very high fidelity and they come easy for us. We then show numerically, because we were unable to prove this. There's a proof for harmonic oscillators that if you combine snap gates with displacements, that you get universal control. And we have numerically shown that the same thing is true for our SU2 rotation combined with this snap type gate. And nicely, depending on the dimension of your system, you need about d-1 gates here to get to an infidelity that is just the numerics of our simulation. So this is where we numerically convinced ourselves that we really only need order of d of these decompositions here, where we do a snap, a displacement, a snap, a displacement, and we go from quadratic to linear scaling. So you need far fewer pulses. And again, the intuition is that you're driving the whole of Hilbert space at the same time, rather than do it sequentially. Yeah? Yeah.
Yeah, so sorry, just to make sure I understand, there's 3 colors here on this lower plot. And so that greenish one is where you cut off at d-2 snap and displacement.
Yes, exactly.
And so you really need to go beyond d-2 to get very high fidelity.
Yes.
Is what it looks like. So there's some funny boundary.
Yes, exactly.
Okay.
Yes, and I think that is real. And actually, in some of our cases for DS8, we sometimes play with that because this is numerics, right? So assuming perfect gates. And sometimes we play with that where we accept that we have some decomposition error and we just do fewer displacement gates to compensate for the, like essentially you don't need the perfect decomposition if you're going to be killed by your pulses anyway.
I see. Okay.
Which, by the way, is something that in bosonic codes I think is common, right? Like you don't always. Sometimes you just approximate the gate. You don't do it perfectly.
Yeah, that's common.
Yeah. So we can play similar games here, and we do believe that this is exact. Like this is just numerics. But yeah, there's games that you can play there. Right. So skipping ahead a little bit, if you're interested, many of these details are in the paper that are in the archive. But we characterize these in a few ways. So one of them is by creating a logical qubit in a spin cat where your logical code states are linear combinations of these coherent states. And then you can do logical gates between this and do this process called randomized benchmarking, where you essentially pick a certain number of gates that you want to do, and you randomize over the types of gates that you do, and then you undo them. And so in principle, you should end up where you started, but the longer you go for the sequence, the more errors add up, and then you go down. And here we characterize that depending on the fidelity, on the dimension here, we can get like fairly high fidelity gates with this. We understand the errors fairly well. We have a few gate optimizations. We don't just do square pulses, but we shape them a little bit so we can do a little bit faster and we can ignore some of the rotating terms. And then what we see is that when we go really fast, we get a 1/time square type scaling, which is consistent with coherent type errors. But if we go really slow, we get something that scales as t, the time linearly, which is what you would expect from energy relaxation. And so encouraged by that type of behavior, we can fit this and find the typical parameters for a simplified model. And then from there, we can estimate if we can improve this fidelity, if we would increase the Q of our system or the T1. And we think we can go about 1 order of magnitude better if we just have state-of-the-art qubits rather than the type of qubits that we had right here, which, keep in mind, our circuits, the way that they look on the chip, look exactly like the IBM circuits or the Google circuits, or like we didn't really add anything special. There's no new materials, there's no new design. And that means that we're confident that by optimizing the materials and the microwave design, we can get to the point of the machines that Google has or IBM has. And that makes us confident to say that it's possible to get here without a lot of work. So I think that that's actually a good benefit of our circuit, of our system. It's not as flashy new, but it can use all the tricks that industry has already developed. So we benefit from that. Right, so finally we did an experiment that I really like, which is we just prepared state 9 and then we watched it fall down as a function of time. And until the longest time, my students refused to actually fit this with rate equations, but I now finally found somebody who did this, because the way that we first extracted our T1s is just by preparing state 9 and watching this decay, and then preparing state 8 and watching the decay of state 8. But now you can see this whole system here. You can look at rate equations and you just prepare the Transmon in the excited state. You watch it tumble down the ladder. You get all the decay times in like one T1 type experiment. You can then plot the scaling, and what you see, this is the bosonic enhancement that I talked about. I will skip some over the details here. We can talk about it later, but actually you can use this to look at Fermi's golden rule and then come up with all the microscopic types of noises that are here and look at the spectral density, and then make plots of, depending on whether the noise mechanism is quasi-particles or Purcell decay or dielectric loss, you can make predictions for how the decay should scale as a function of initial state. And what we find is that we are most consistent with dielectric loss, which is just on the surfaces, 2-level systems that are absorbing our energy. But because every transition is at a different frequency, you get this characteristic decay. And we think that we're limited by that, which is consistent with what we thought we were going to be limited by. We cannot fit to this model because there's too many parameters, but we're also working on some smarter way to do that. So that's the last part. And to me, this also shows that you can do some fun physics with these systems as well. We've talked about this separately, but we're really interested in like the real like quantum noise model of this, and it's something that we're measuring. And you also brought up ionization. This is also a great tool to just drive it really hard and see how you get transitions that happen during readout that actually the whole field is seeing, even if they do qubit readout. So you get these multi-photon type transitions, and that actually limit how fast you can read out, even if you do qubit readout. And we have a system that can actually measure that because we have these many levels. So we have a project, if you're interested in this remark, there's a presentation at March meeting that looks into this. We have a collaboration with Alexander Bley at Sherbrooke to look into that. So that's just to say that we can actually do interesting Transmon physics with our devices as well. I didn't touch upon this, but we can also test it to test things like Josephson harmonic model. Again, more remarks for the experts here. But more generally, what we have shown is that our single qubit control abilities look fairly promising. We are encouraged that maybe you can get advantages for qubits if you can couple these together. So we're starting to look at 2 qubit gates. We're also exploring ways to do error correction and analog simulation. The one remark I wanted to make is that the main limitation we have is that we have a limited anormalicity if we go higher in dimension. And there's one circuit that is a slight adjustment to this, which is just adding an inductor here, which, depending on the parameter regime between the inductor, the capacitor, and the junction, they come with different flavors and different names. But the regime that we are interested in, it's called the inductively shunted Transmon. And then you can kind of go around this trade-off of having many levels and not so high anormalicity, and actually create a circuit that has both many levels and a very high anormalicity and very low charge noise. And the first step for that was to make this inductor here. You could do it with materials. We made it with geometry. And this was a paper that we published showing that you can make these spiral resonators with fairly high Q and very high impedance, which is a very high inductance. And we're looking at making these both with to make ISTs, so better qudits, but also to couple these maybe to spins or other defects. So that's another line of research that we're working on that I won't talk about. I wanted to highlight briefly, and there's a paper in PR Reply that recently came out where we study these resonators and their magnetic field behavior. Right, so summing up, I'd like to thank you for your attention and the whole group here. all the people working on all these projects. And I just briefly wanted to take the time to say that we are represented in APS Global Summit meeting in LA. If you're interested, these are the details. And then finally, we have a quantum conference coming up in Rochester in the summer that is just opening up registration. So if you're interested in talking quantum at Rochester, we have a really nice lineup with many of the people in the field coming. So please come to Rochester in summer and reach out to me or keep an eye out for announcements there. And with that, saying that all our devices are fabricated by Lincoln Labs and we're very thankful, I would like to thank you for your attention and take any questions.
So we have time for like questions. Yes, I don't wanna... So I have one question, which is why go to a multi-level system? Like, so what's the advantage there compared to having a two-level system? How to implement it into?
Yeah, so the advantage is that you don't have to entangle stuff.
Okay.
Or less. Yeah. So like the easiest example or the easiest comparison is if you have 8 levels and you have one DSA qubit, you could also make 3 qubits coupled together. But then if you want to do unitary operations between an 8-level system, there's by definition no entanglement in that system. So it's all local operations.
Right.
And in terms of quantum computation, if you think about the unitary, it has the same power as doing operations between 3 qubits. But there's 0 entangling gates. And entangling gates are the hardest thing there is. Another way to say this is that it has better connectivity. Yeah.
Sorry, I have a question about that. So there's a subtlety, I think, maybe it's not subtle, but I don't understand it. So if I have so I've heard many people make comparisons. Oh, I have a qudit, and it's like n levels, and then I could just make up qubits, and it's kind of like that. Except the independence of readout is different, right? So if I have bunch of qubits, I can read out this one and not that one.
Yep.
And if I have a qudit, I can't do that.
Yep.
What are the consequences of that?
Yes. So my argument is all in unitary evolution land. So then there's no consequences to that because I didn't talk about readout.
The readout does matter in quantum technology.
So if you need to do error correction, right? I agree. And then the key there is that if you now, I'm going to come at an answer that agrees with you completely, which is if you want to do error correction in a system like this, it might be true that you need to engineer a measurement that is more complex than if you were to do this in a qudit. I think that is like, if you now were to say that I take so suppose that you now think of this 8-dimensional system, right? And now you think about doing a parity measurement there. Then that parity measurement might be difficult depending on how you think about it. My first answer is, I don't think that I would take D to infinity and do my whole computation in a single qudit. I think there's some trade-off there. And then if you have, for instance, a qudit that has a nice number of qubits encoded in it, then you need to define the syndrome measurements that you want to do. And now you need to find a way to implement that. And if that's a binary syndrome measurement, you could couple this to an ancillary qubit and then get good control between that qudit and that ancilla qubit. And then you need some entangling operations to map the syndrome measurement onto the ancilla, and that might be more complex.
So what you're saying is that someone could imagine a path, but at the moment that path isn't flushed out.
Well, no, I'm trying to give you the no. I don't agree with that because for the bosonic case, right, which is an easier case to give the argument. Whether this is a good idea or not really depends on the details. So it depends on what the noise model is, and it depends on what the operations are that are easy and that are hard. The example I gave you, I think I gave it because it agrees with your point, so it nicely illustrates the problem, but it's not the best way to go about it. So I think my answer would be, it would be a mistake to think of this as purely a qudit that encodes many qubits, and then only do everything that you would do on a qubit.
Oh, that.
So you want to find stuff that's easy to do on qudits or on multi-level systems. And for bosonic codes, for instance, this has been very well thought out. So then the operations that are easy to do that are natural are displacement gates and squeezing operations. And you have to take into account the noise, right? It's not just how well can you do one particular operation, it's how does that commute with the noise model that you have. And so now you need to design the type of error correction code such that it matches well with both the noise and the things that you can do well. And maybe the long and the short answer to your question is, in doing that, you will find other trade-offs for qudits than you will find for qubits. And you need to be very particular. Yeah. But since you asked specifically about measurement, like measuring operators in a qudit might be more difficult. But also, I mean, maybe you can engineer measurements where it's not, right? Like, yeah.
One small idea about that is like, in a typical qubit, you measure on one basis. And how do you measure another basis? Well, you just rotate it, right?
Of course.
Yeah. So here, he has full universal control over the qudit, and he measures all of the levels. So you can engineer other unitaries that map whatever starting basis to these Fock states, and then you can just measure. So in principle, anything is possible, but it's just what's the right thing to do.
Well, and what's the coherence? Because we know that there's loss during the measurement time. So if measurements were all instantaneous and the rotations were all instantaneous, that would be completely correct. But it's a big, big space. So of course, measurement is going to be just as hard as other things.
If you have 3 qubits, the probability of decay is also 3 times higher than any one. And it's not that different here, right?
Yeah, I agree. There's subtleties. I think that was the answer to the question.
Yeah. Which is,
Subtleties.
I mean, yeah.
Great, thanks.
Okay, so we'll thank our speaker once again for this amazing talk. And we will see you next week for a talk by Professor Rana.